Here you can see the current balance apparatus. On the left, there is our DC power supply. Here, on the right, is the current balance itself. Tyler is now going to attach the wires to the DC power supply so that the current flows through the two wires of the current balance in opposite directions. Tyler's now going to adjust the balance's counterweight so that the floating wire stays suspended a fraction of an inch above the fixed wire. You can see it is free to float up and down and therefore will be sensitive to small forces from the two currents. The laser is placed on this block so that the beam is angled up and can hit the mirror on the current balance. Here the mirror is shown. The laser is adjusted and so it hits the center of the mirror. The width of both of the wires can be measured with the dial micrometer. The distance between the two wires can also be measured with a dial micrometer. To accomplish this, we actually measure the outside diameter of both and then subtract the diameter of one wire from that. What we're really interested in is the distance between the centers of the two wires. With the arm floating and the laser reflecting off the mirror, the laser spot moves up and down as the arm oscillates. A piece of paper can be placed on the chalkboard and the equilibrium position of the laser can be marked. When mass is added to the pan on the floating arm, the whole assembly moves slightly downward, tilting the laser spot down on the board. The current from the DC power supply can then be adjusted so that the repulsive force from the wires is exactly enough to lift it back up to its equilibrium position, balancing out the force from the small weight. Here you can see the current being turned up and the laser spot returning to its equilibrium position. At this point, we know that the force of the repulsion of the two wires is equal to the force of gravity from the small mass.